Hello and welcome to Calculus 1. Now the first chapter in Calculus is going to be on limits. And then chapters 3 and 4 on derivatives. Chapter 5 in Calc 1 will be on integration. But then also chapters 6 and 7 in Calc 2 will be integration again. So one chapter on limits, 2 chapters on derivatives, and then 3 chapters on integration if you include Calc 1 and Calc 2. So before we go and talk about limits, what is calculus? Calculus is a study of change. Things change all the time. Within a day, you are tallest when you wake up, and you are shortest when you go to bed. Because throughout the day, you walked around and your joints slightly compressed. As you drive from point A to point B, the amount of gas that is getting burned from your gas tank is making your car slightly lighter as you move along. We can measure these things. Same thing with your weight. You should be the lightest when you wake up in the morning because your body was processing a lot of energy to keep itself functioning while you were passed out. So you wake up the lightest and tallest, and then during the day you become heavier and shorter, and then you pass out again, and then, right? So it's a cycle. These things, right, are noticeable if you measure them, and we measure them with calculus, because calculus is a study of change. Pretty much every single concept that we have on our planet is described in some form, shaped by calculus. Talk about economics, talk about engineering and physics and all of the STEM to put everything in one, but also you can take a look at the environmental sciences and think about decomposing the garbage and the rate of change at which garbage or the nuclear waste decomposes and things like that. So calculus measures pretty much anything. If the stuff is changing, calculus measures it. Calculus consists of limits, derivatives, and integrals. And the chapter 2, what we are starting right now, is the chapter on limits. So what is the limit? If you ever had calculus before, let's say high school or so, or many moons ago, probably this was one of the most confusing things. Because people want to be fancy and they don't want to tell you the bottom line. And I tell you the bottom line. What's limit? Limit is simply the y value when you compute the function. That's what the limit is. So it's just the answer, the y value, the computation. So if you have a function, say f of x equals to x squared minus 1, and I ask you what is f of 3, you will say 3 squared minus 1 is 8. So this is your pre-calculus. Well, the answer using the limit is also going to be 8 because I just told you the limit is the function answer when you compute the function. So limit of x squared minus 1 as x goes to 3 is going to be 8. Now you might protest and go and say, but why, if it's the same thing, why we have it? Well, it's not producing that answer in the same way. And it's far more powerful than the calculation on the left. You see, calculation on the left is going to go through -1 over here, and then if you go to 3, nah, too far. Now this graph is terrible. Let's make it wider. So if you go to 3, you will go up, and then you will bounce off, and that's where your 8 is. So in order to calculate with pre-calculus, you actually have to have this point here, which is 3, 8. You have to have that point defined. If you have open circle, the line from 3 will shoot through that opening and never bounce to give you answer of 8. So in that respect, pre-calculus cannot solve that problem, but limit can, which is why limit is so powerful and why we learn it. So we are going to now go and understand what is the way that the limit computes things. So what is the limit? It's just a fancy way of computing the y value. That's all it is. Fancy way of computing the y value, and we are done with the definition for now. We will revise that obviously and put more mathematical rigor as we go on, but the intro talk is, yeah, fancy way of computing values. So now on the limit side, I'm going to draw the same graph, and I'm going to say here is my input 3 and here is my output 8, because we already know the answer, so I'm just going to draw that. Now these two graphs look the same, but what is the way that calculus used to calculate this? Calculus has this over here. This is read as x approaches 3. So x value, x input values are approaching 3. So I am going to approach 3 from the left, and I am going to approach 3 from the right. These are the only two ways in which I can approach number 3 on x-axis. Now, how does this motion of approaching 3 on x-axis reflects to the function in y? Well, note this. As you approach 3, all of the newly rising x values are producing these y values, which are climbing towards 8. Do we see that motion? So this one over here produces this one over here. This one over here that is closer gets you closer. The closer you are getting to 3 on x-axis, the closer you are getting to 8 on y-axis. So the motion on x-axis causes the motion towards the y. From the blue side, we are going to approach this way, and you see that as they simultaneously squeeze onto 3, the y squeezes onto 8. Guess what? In this calculation, we never calculated at 3. We calculated at all infinity of the points around 3. We never calculated at 3. Now, what is the only point that we calculated in pre-calc? 3, right? So you see that this is completely backwards. In pre-calculus, you calculate at the single point because you plug it in a formula and you get the answer. Calculus said, no. You get to calculate infinitely many answers to the left and look at the trend. And the trend is screaming, oh, I'm going to 8. Then you look at the blue approach. I call this Romeo and Juliet, by the way. Blue approach goes down the line. You know Romeo and Juliet, right? Yeah, did I do it? Right. That was the highlight. At least for me. Family nicely. Oh, you don't mess with. Are you dead? That's what happens when you don't listen to the older, more experienced people. You die. Because you don't know. Yeah, read the whole thing, see what happens. Anyway, so Juliet is going towards the 3. She's climbing up the function, going towards 8, because they're going to meet at 8. And the Romeo, right, is going from the other side, and there they go. They meet, right? So it all worked out. Now, I'm going to do the same calculation, not graphically, but numerically. So what I'm going to do is I'm going to make the chart of values. Yeah, blue. So these be my x's and these be my y's, right? 3 values. And 3 values. So what do I have? Well, I have values that are approaching 3. 2.9 is 10 cents away. 2.99 is closer to 3, right? And then 2.999 is closer still. That's a cheap way to get this. On the other side, let's be 10 cents away. Let's be 1 cent away. And let's be 1/1000 of a cent away. I mean 1/10 of a cent away. Now, summon your abacus and calculate this. Remember, you're not allowed to calculate the 3. You have to calculate the other 6 numbers. And those 6 numbers better scream 8 when you look at the pattern. Otherwise, your calculator skills are questionable. So we have 2.9 squared minus 1 to get 7.41. 2.9 squared minus 1 is 7.9401. So you already see that we are getting better. Because we had 7.4, now we have 7.9. See how it's getting closer to 8? Let's see with a 2.999 squared minus 1. It is 7.994. Well, that's better than 9.4. Now I have 9.9. So do we agree that Juliet's side is going towards 8? Yeah, we are, right? All right, Romeo. 3.1 squared minus 1 is 8.61. 3.01 squared minus 1 is 8.06. All right, do we see that it's getting better? It used to be 8.6, now it's 8.06. That's much better. And finally, we have 3.001 squared minus 1 to give us 8.006. Well, Romeo is also screaming 8. If it walks like a duck and quacks like a duck, it's a duck. Exactly. Don't worry about it. There you go. Limits done, achieved. That's. I hope you're not disappointed, but that's it. Approach from the left, approach from the right. If they go to the same number, that's the limit. If they go to different numbers, that's not the limit, and that's it.
So can you put the decimal place and go infinitely with that?
Yes.
Therefore, it would eventually get to that number.
Yes. In infinity, we'll get to that number. So, yeah. So this is the way the limit works. Yeah, we did only 6 calculations out of infinitely many that we were supposed to, but let's be efficient with time, right? We're not else. So the limit is going to be used to define derivatives and integrals eventually. So we have to have a good handle on limits. What you see in this section now is the most fundamental way to calculate any limit out there. Now, this is very inefficient because you don't graph by picking and calculating points. But that's the first thing you learned, right? Pick x's, calculate y's, plot the dots, connect them. Middle school, right? You can graph anything that way. But we spend time teaching the linear function, quadratic, exponential, and their graphs, so you don't have to sit there and compute y values given x so you can plot. You just know what the graph looks like from immediately from what is written on the page. So the same goes now for limits. In the next section, we are going to learn algebraic ways to solve limits. Right now, we're doing the middle school way. And the middle school way is pick your x's, compute y's, and then look at the pattern. And if the pattern is telling you that it's converging to a certain number, that's the limit. If it goes to different numbers, well, guess what? No limit. Let's take a look at that. Say you have a piecewise function which says f of x is equal to x for all x's bigger or equal than 0, and x minus 1 for all x's smaller than 0. Well, we are going to graph this. We are interested, obviously, at what's happening with the limit at 0. All right, graph. Well, line y equals x is a 45-degree line, but I only need half of it because it's only defined for x values that are bigger than 0, which is this side of the graph. So we are not going to draw this part of the line here because we don't need it. Now x minus 1, oops, sorry, this is the closed circle, open circle at -1, and then this. So what is the limit at 0? Now we are going to solve this problem graphically and numerically. Romeo and Juliet approach 0 from the left, which is going up to the line, going up to -1. So Juliet's approach is -1. Romeo approaching from the right, going down this line, ends up at 0. Do we see that? Remember, we are looking for y values as you are approaching, right? So Juliet is approaching 0, her y value is approaching -1. Do we all see that? So this is less than -1, I say more than negative, or less than -1, less than -1 as this reaches 0. Romeo goes from the other side, down this line to 0. Do they meet? No. We say limit does not exist if they don't meet. Because there's no answer. You can't have two answers at the same time. Well, electrons can, but you can't. Are you here or are you home? Or somewhere else? Actually, no, you can pull that off because you can be here and then mentally project yourself anywhere, but let's keep the physical appearance. So these do not match. Limit does not exist. D&E. Okay, say you're not convinced. Immediately, what I do is the chart, right? So this is your 0. Pick your 3 numbers on the left, pick your 3 numbers on the right. So to be far away from 0, say 10 cents, that's going to be negative 0.1. And then you get closer, this is Juliet's side, right? At negative 0.01, because that's closer, and negative 0.001, closer still. Romeo side, 10 cents away, 1 cent away, 1/10 of a cent away, getting closer. Okay, Juliet, what do you have? Well, she's mirroring these and subtracting 1. So, negative 1.1, negative 1.01, negative 1.001. Romeo has the same numbers because y equals x. On the Romeo side, y equals x, right? Look, Romeo side, y equals x. So we get to copy Romeo numbers. And as you can see, Juliet is going to negative 1, and Romeo is going towards 0. They do not match. Limit does not exist. So we write limit x goes to 0 of f of x equals does not exist, because the left side and the right side do not match in the value like it matched earlier, both giving us 8. Cool? Of course, cool, it's calculus. So now we are going to write the most important theorem of chapter 2. Theorem 2.1. Now, what are theorems? Before I write this, guys, theorems are what you use to solve problems. Those are tools. Definition is what it is, and we'll define limit later in mathematical terms. So definition is what it is, and theorem is how to solve the problem, the tool that you use. This one will be dragged to chapter 2, Calc 2, and Calc 3. Probably the most used definition, a theorem, in all of calculus. What does it say? Well, it says if the limit of f of x as x approaches a minus, that's the left approach, is the same as the limit of f of x as x approaches a plus. So if those two have the same value at the end, then the overall limit x goes to a, this is from both sides at the same time, of f of x is going to be that L. Remember, Juliet's approach from the left, which is this minus here, gave you 8. And the Romeo approach from the right, the blue one, gave you 8. So 8 equals to 8, and the whole limit was 8. We have to finish this theorem. It says, otherwise, limit does not exist. Which means, if this is not equal to that, and that was the second example. Juliet went to negative 1, Romeo went to 0. Negative 1 and 0 are not the same, limit does not exist. So, the second part of this theorem says, otherwise, limit does not exist. This solves all of the problems. in calculus for limits. You look at the left approach, right approach, they have the same number, that's the limit, they have different number, different limit. If you don't know how to solve it algebraically, you're going to sit there like a peasant and calculate the points. Yes?
So if it's a piecewise function that in the x, like the way we just did, basically, like it would just not exist?
For this piecewise function, sure. But I can make a piecewise function that connects.
Yeah,
and then it would exist, right?
But like if the number, like you have x and then x minus 1.
Uh-huh.
So it was like x was...
I can have x and x squared.
0 and then 1 was approaching -1. So that was... But you could have it so it's like a negative and a positive, right?
Yes.
And
so
then it would be the same.
Uh-huh.
Okay.
So here is an example of what you're asking. The lecture is over, by the way, but let's answer this question. So what happens with the piecewise functions? Can we have a piecewise function to have a limit at the break where the pieces connect? And the answer is yes. If those pieces connect in the same point, you will have a limit. So if I go and say f of x is a piecewise function, x plus 1 for x is less than 0, and let's say x squared plus 1 for x is less than 0, note that I don't even have the equal sign. The graph for this is going to look like this. Open circle here because there is no equal sign on any of these sides. Romeo side has the... Oh, sorry. This open circle happens at 1. On the Romeo side, you have a parabola. On a Juliet side, you have y equal x. So now, when Juliet approaches from the left, she is approaching number 1. So Juliet approaches number 1, and Romeo's approach going down this line is going to approach again number 1, and the overall limit is number 1. So piecewise functions could go anywhere. Can go one way or the other way. It only depends whether they connect at this point when you draw the graph. You can also detect all of this with the graph, with the chart of values. You compute your y values with the x values you picked. Now you have to pick x values so they're actually approaching the number that you want to approach. Now you can't pick random stuff, right? You're approaching 3, you can't pick 7, 10, and 13 because they don't approach 3, right? You've seen me, the way I used sense to make sense of the approach. Bueno? Yes?
Could this also be used to find intersection points between multiple, say, equations?
No, that's going to be solving equations, which we are actually going to talk about. So we are going to solve equations graphically, yes. But this is not it. This is computing the y value. When you're solving equations, you're looking for x value, right? So the limits are solving y values, so they're completely disconnected. But we'll go through that as well. Good question. Anything else? No? Well, I'm sorry we missed your mark. Registrar suggested time apparently is 8:50. It's 5 minutes free of charge, so enjoy it. Okay, bye.
Thank you.